Welcome back to the deep dive. Today we've got a really fascinating stack of highly specialized manufacturing data to get through.
It's a really critical topic for anyone in the industry.
Right. And our mission today is basically to decode what is a make-or-break business decision for CNC operators. So imagine for a second that you are managing a high-volume production line, right? You've just secured this massively profitable contract to machine these really complex metal parts.
Which is the dream, obviously.
Exactly. It feels like a huge win. You're ready to scale up.
Yeah.
But then maybe a few weeks into production, everything just grinds to a halt.
Yeah, the nightmare scenario.
Right. You end up losing the job, or even worse, you're actively destroying your ridiculously expensive cutting tools. And all of it, literally all of it, is because of one single purchasing error.
Yep. You bought the wrong CNC lathe turret.
Exactly.
It's a devastating scenario, but honestly, walking onto factory floors, you see it happen way more often than anyone really wants to admit.
Oh, I bet.
Yeah, because the difference between a successful, highly profitable run and a total mechanical disaster, it frequently comes down to the architecture of that one specific component.
Yeah.
Like, choosing incorrectly means you are essentially setting cash on fire, you're dealing with constant machine crashes, or you're just finding yourself completely incapable of delivering the complex geometries your client is actually paying for.
And that brings us directly to our mission for today's deep dives. We are going to decode a highly technical but fundamentally critical decision that impacts your daily operating costs. We're looking at choosing between a standard servo turret and a power turret for a CNC lathe. And we are going to extract the absolute most vital differences from the source material here, specifically looking at indexing speed, mechanical rigidity, and long-term reliability.
Because understanding these differences it's non-negotiable, really, if you're making capital equipment purchases for a production line. Buying a lathe without the correct turret architecture is basically trying to build a modern house with only a hammer. Like, you might desperately need to drive screws, but you are stuck holding a tool that's engineered exclusively for nails.
That is a great way to put it. Okay, let's unpack this core distinction, because before we get lost in the weeds of, indexing metrics and torque values.
Which we will get into.
Oh, definitely. But first we have to establish the foundational, functional difference between these two pieces of machinery.
Right.
And stripping it down to the basics, the primary divide is all about tool rotation.
Exactly. We are talking about the difference between static tools and live tools. Those two categories dictate the entire mechanical layout of the machine.
Okay, so let's look at the servo turret side of the equation first. This system uses a high-precision servo motor, and it relies on a digital encoder to achieve just incredible positioning accuracy.
Yeah, very precise.
We're talking about hitting a repeatability mark of 0.0001 millimeters effortlessly.
Right.
But, and here's the major constraint, it holds only static cutting tools.
Yeah.
It is engineered purely for turning, grooving, and boring. Like the metal workpiece itself spins at high speeds, but the tools, entirely stationary.
Which contrasts completely with the internal architecture of the power turret.
Right.
Because a power turret is built for what the industry calls turn mill composite machining.
Okay.
If you actually open up a power turret, you find a highly complex internal transmission. You have an internal motor, mechanical clutches, specialized drive shafts, transmission gears.
There's just a lot going on in there.
Exactly. And all of this extra internal machinery exists for one specific reason: to deliver rotary power directly to live tools, meaning tools that actively spin, like milling cutters and twist drills.
Right. I was actually trying to conceptualize this, and it reminds me of a high-end restaurant kitchen.
Oh, I like where this is going.
Yeah, so think of the servo turret as this impossibly fast, laser-focused sous chef who only chops vegetables.
Okay, yeah.
Right? They have the sharpest knife in the building. They hit the exact same cut every single time, down to the microscopic level. But they only chop right.
The power turret, however, is the entire multi-station kitchen. It chops the food, sure, but then it moves right on to cooking the meat, simmering the sauce, and plating the final dish.
I really like that framing. And the reason that multi-station kitchen capability matters so heavily in manufacturing comes down to a critical operational concept.
Which is?
One-time clamping.
Ah, right.
This is where the power turret starts heavily manipulating your bottom line. If you put a power turret on your floor, you load your raw metal bar stock into the machine's chuck exactly once.
Once. That's it.
That's it. The machine turns the cylindrical shape using static tools, But then, without ever unclamping or removing the part, it engages its internal gears to drive a live milling cutter.
Wow.
It creates flat sides and then spins up a live drill to plunge off-center holes.
So it literally executes the entire manufacturing sequence in a single setup.
Exactly. You eliminate secondary milling operations completely. Think about the cascading effects that has on a factory floor.
Yeah, I mean, you're saving so much time. And money. You're no longer taking a partially finished, greasy part out of the lathe, physically moving it across the building, and building an entirely separate, expensive metal fixture just to hold it in a standalone milling machine.
Which would cost a fortune.
Right. You save all the capital you would have spent on extra fixtures. But more importantly, you maintain mathematically perfect alignment because the part never moved from its original 0 point.
Because it's still clamped.
Exactly. The moment you unclamp a part and move it to a second machine, you introduce compounding geometric errors. One-time clamping eliminates those errors and massively increases your daily output.
Okay, honestly, that makes the power turret sound like an absolute no-brainer.
It does, right?
Yeah. If I am a buyer looking at these two machines,
Yeah.
and the power turret can do everything, turning, milling, drilling, why would I ever write a check for a servo turret?
Well,
Shouldn't a manufacturer just buy the machine that handles every possible operation?
the physical reality of mass production makes that a pretty complicated choice, actually. If you look closely at the specifications, the answer really comes down to the absolute industry obsession with indexing speed.
Indexing speed.
Yeah. The time it takes for the turret to rotate from one tool to the next.
Right, so we are talking about non-cutting time.
Yeah.
The time where the machine is doing absolutely nothing to make you money.
Exactly.
And looking at the raw data from our sources here, a modern servo turret uses a very streamlined, lightweight physical structure. Because it lacks all those heavy internal milling gears we talked about, it can change adjacent tools in 0.1 to 0.25 seconds.
Mm-hmm.
And if it has to execute a diagonal tool change, like jumping all the way across the turret face, it takes less than 0.5 seconds.
Yep, it's incredibly fast.
But I have to push back here.
Okay.
Are these tiny fractions of a second really worth stressing over for the buyer? I mean, if I am dropping hundreds of thousands of dollars on machinery, does a tenth of a second actually justify choosing a less versatile machine?
What's fascinating here is that if we run the operational math, those fractions of a second absolutely dictate profit margins.
Really, just fractions of a second.
Oh, completely. Let's say you're manufacturing simple aerospace fasteners, or maybe medical bone screws. You might be churning out 100,000 of these identical parts every single month.
Okay, that's a lot of volume.
Right. So if you save half a second on every single tool change, and there are, say, 5 tool changes per part, you are suddenly saving hundreds of hours of non-cutting time over the course of a year.
Oh, wow.
Yeah. Those saved hours equal thousands of extra parts produced at zero additional overhead. That is pure, unadulterated profit margin.
Okay, so the math heavily favors the servo turret when you scale up simple, high-volume parts.
Exactly.
And the mechanics behind how it achieves that speed are honestly fascinating. It uses a closed-loop servo system that constantly calculates the shortest bidirectional rotation path. So instead of always indexing clockwise and wasting time spinning all the way around the block, the computer reads the encoder, figures out the shortest physical distance to the next required tool, and just snaps directly to it.
It gets even more mechanically advanced when you look at the physical locking mechanism, actually.
Oh.
Yeah, to hit those 0.1 second tool changes, servo turrets utilize non-lifting indexing.
Okay, let's break that down for a second. How exactly does a heavy metal turret rotate without disengaging its lock?
Well, it relies on a highly engineered 3-piece coupling system.
Okay.
See, in older machines, to change a tool, the entire heavy turret head had to physically heave outward.
Like push away from the machine.
Exactly. It had to move actually away from the machine body to unlock its gears, then slowly rotate and then slam back inward to lock. It was this massive, clunky movement.
That sounds slow.
It was. But with modern non-listing indexing, the internal 3-piece coupling allows the locking rings to separate just enough to rotate radially without pushing the entire massive tool block outward. It simply clicks, spins, and instantly locks.
Wow. Now, if we compare that lightweight agility to the power turret, things slow down a bit. Because a power turret also uses servo motors for its rotation, but it is carrying around significant mechanical overhead.
So much more weight.
Right. It has to physically rotate the heavy live tool transmission, the internal clutches, the drive gears, all that rotational mass basically acts as a penalty.
Yeah, the indexing action is fundamentally slower. You simply cannot spin heavy, complex masses as fast as you can spin a hollowed-out, lightweight servo block.
Makes sense.
And this is where the operational strategy really comes into play. The power turret easily absorbs that indexing penalty if you're producing complex components.
Right, because you aren't transporting the part to a second milling machine.
Exactly. You might lose a quarter of a second every time the turret rotates, but you save 20 minutes of handling time, fixture setup, and secondary machining alignment.
That is a massive trade-off.
It is. The overall part cycle time for something like a complex automotive shaft drops drastically when you never let go of the metal.
Okay, so you are trading pure indexing velocity for complete start-to-finish processing.
Yeah.
But whether you choose the lightning-fast servo turret or the heavy-duty power turret, there is one reality from the data we have to acknowledge. Both of these modern electric options completely obliterate the old fluid-driven hydraulic turrets.
Oh, it's not even a contest. Hydraulic systems were the standard for decades, but the physical limitations of fluid dynamics they cannot compete with electric servos.
Why is that?
Well, with hydraulics, your indexing speed literally changes throughout the day.
Wait, really?
Yeah. When the oil is cold in the morning, it's thick and sluggish, making the turret turn slowly. As the machine runs and the oil heats up, the viscosity drops and the turret speeds up.
That sounds like a nightmare. You cannot build a highly precise, highly predictable manufacturing process when your machine's speed depends on the temperature of its hydraulic fluid.
Exactly. Electric indexing gives you the exact same microsecond performance at 8 a.m. as it does at midnight.
Right. Okay, so we have firmly established the speed and efficiency metrics.
Yeah.
But velocity is utterly useless if the machine structure starts shaking violently the moment a cutting tool touches hardened steel.
Yeah, that's a problem.
Here's where it gets really interesting, because we have to talk about the physics of metal pushing back against metal. We need to explore mechanical rigidity and loading capacity.
And this is an area where a lot of shops learn a very, very expensive lesson.
Oh, sure.
Because rigidity is the structural characteristic that prevents vibration. And vibration, specifically what machinists call chatter, is the absolute enemy of both dimensional precision and tool life.
Okay, so let's analyze how the servo turret is constructed. It features a one-piece cast iron body mated to that high-precision three-piece coupling we discussed earlier. And this architecture provides excellent static rigidity. Like if you are doing precision turning, where the part is spinning smoothly and the static tool is just peeling off thin ribbons of metal, it is structurally perfect.
Right, it's great for that.
But you have to remember, it outputs zero rotational torque. It is fundamentally not engineered to drive a spinning milling cutter through a solid block of titanium.
No, absolutely not. And that is exactly where the power turret steps in with pure brute force muscle.
Right.
The fundamental design priority of a power turret is maximum mechanical stiffness and high radial and axial load capacity.
Okay, so how do they build it differently?
Well, to achieve this, it utilizes a heavily reinforced disc structure. Instead of just a standard locking ring, it uses large diameter couplings paired with massive hydraulic clamping force to lock the rotating head in place.
Wow.
Yeah, this upgraded architecture improves overall structural rigidity by over 20% compared to standard servo turrets.
Okay, I want to offer an analogy here to help visualize this difference in rigidity. Think about the servo turret as a lightweight sports car.
Okay.
It's perfect for agility and precise handling on a really smooth track, right? But if you need to pull a heavy trailer through the mud, which in our machining world represents aggressive face milling and cutting hard steel, you can't use the sports car. You need the reinforced brute force torque of an SUV, and that is the power turret.
That's a perfect way to look at it. And expanding on that SUV comparison, that rigidity directly prevents vibration.
Because it's so heavily built.
Exactly. If a manufacturer is dealing with complex automotive shafts and sleeves that require heavy roughing forces, the power turret's live tool spindle outputs up to 150 newton meters of torque.
150 newton meters. Let's contextualize that force. That's roughly the amount of rotational force you'd use to tighten the heavy lug nuts on a full-size pickup truck.
Yeah, it's massive.
Having that much rotational power inside a precision mechanism that is accurate to 0.001 millimeters is just an incredible engineering feat.
It really is. And to transfer all that torque without slipping, it supports heavy-duty interfaces like BMT55 or ER32.
Right, and BMT stands for base mounted turret, which basically means it uses large bolts and precision keys to bolt the live tool holder directly to the face of the turret.
Exactly.
So this massive surface area contact ensures that when you apply 150 newton meters of force to a spinning milling cutter, the tool holder doesn't twist or slip at all.
Right. And without that heavy-duty deformation resistance, the cutting forces would completely overwhelm the turret locking mechanism.
Which causes the chatter.
Exactly. Your carbide end mills would snap in half, your part surfaces would look terrible, and your scrap rate would skyrocket. The power turret is built to take that punishment.
Okay, so what does this all mean for the long game? Because signing the purchase order for the machine is really just day one.
Very true.
We have to pivot to what happens after this turret has been running 3 shifts a day in your factory for 2 years. What do all these complex internal gears and high-speed servo motors mean for your daily operating costs, your maintenance schedules, and your actual monthly electricity bill?
Well, if we connect this to the bigger picture, the total cost of ownership, or TCO, is frequently where the real manufacturing profit is either made or lost.
Absolutely.
And this is an area where the two turrets offer completely divergent long-term financial profiles.
Let's start with the servo turret. From the data, it sounds like an absolute dream for the maintenance department.
Oh, they love it.
It boasts exceptionally low maintenance needs. Because it has that beautifully simple, compact internal structure, there are very few moving mechanical wear parts. You don't have gears constantly grinding against each other. It mostly just requires routine electronic sensor checks and basic lubrication.
Yeah, and the energy profile is equally fascinating. The servo system only consumes significant electrical power during the actual fraction of a second when it is physically indexing from one tool to the next.
Oh, really?
Yeah, when the turret is locked in place and the static tool is cutting the metal, the indexing motor is essentially asleep.
It's not drawing power.
Barely any. It isn't constantly drawing heavy parasitic power from your grid. That actively drops your daily electricity bill and significantly lowers your baseline operating costs over a 5-year lifespan.
And despite lacking heavy mechanical locks, that closed-loop digital encoder system maintains its 0.001 millimeter repeatability for millions upon millions of cycles.
Right, without mechanical degradation. That lack of degradation is key. Because it relies on digital pulses rather than pure mechanical stops, it doesn't suffer from the physical wear and tear that slowly ruin the accuracy of older machines.
But then we pull back the curtain on the power turret, and the long-term reality shifts quite a bit, doesn't it?
It does. It naturally demands more rigorous preventative maintenance simply because the laws of physics demand it.
Because of all those moving parts.
Exactly. You have that highly complex internal drive system, the transmission clutches, the rotary drive shafts, the specialized bearings, the gear meshes. All of these components act as potential wear points that require constant lubrication management and periodic mechanical adjustment.
And what about the power consumption?
Well, because the power turret is actively driving spinning tools through hard material, the internal live tool motor is constantly drawing heavy electrical loads during the actual milling and drilling cycles.
Right.
So your baseline energy operating costs will simply be higher.
But even factoring in the extra maintenance requirements and the higher power bill, the long-term reliability of a properly maintained power turret is still exceptional, right?
Oh, absolutely, because you have to remember what you are saving your maintenance team from. Even an internally complex electric power turret is a massive upgrade over the absolute nightmares of those old hydraulic systems we touched on earlier.
Right. With the older hydraulic milling systems, you were dealing with constant oil breakdown, thermal expansion issues, replacing clogged filters, and just the endless battle of diagnosing and fixing leaking hoses.
The maintenance hours spent just keeping hydraulic fluid clean and contained were staggering.
I can't even imagine.
So while the power turret does require more mechanical upkeep than the cleanly electric servo turret, both of these options give you a drastically cleaner, more predictable factory floor.
And you really have to factor in the maintenance reduction of that multi-station kitchen effect we talked about. By utilizing a power turret, you are essentially combining 2 machines into one. You aren't paying a technician to maintain the moving parts, cooling systems, and electronics of a lathe ND, a totally separate standalone CNC mill. You are consolidating your preventative maintenance into one highly capable turn mill envelope.
And that consolidation is the ultimate win for factory reliability. By reducing the number of times a part has to be moved and reducing the sheer number of separate machines required to finish a product, you dramatically shrink your margin for error. You ensure that you can deliver geometrically perfect, highly complex parts to your customers on time, without relying on a fragile daisy chain of different machines all needing to operate flawlessly at the exact same time.
Okay, so to bring this massive breakdown together and give you a concise, actionable recap for your own production strategy, it all comes down to evaluating the specific geometry of your parts before signing that purchase order.
Right.
If your primary goal is purely high-speed, high-volume precision turning, like producing hundreds of thousands of simple medical devices or aerospace pins where every microsecond of non-cutting time destroys your margin,
Yep.
you must buy the streamlined, lightning-fast servo turret.
Yes. However, if you are taking on complex, heavy-duty turn mill contracts, parts that require aggressive material removal, milling flat hex sides, plunging off-center holes, and dealing with tough, hardened steel alloys.
You need the big guns.
Exactly. You absolutely must invest the extra capital into the structural rigidity and 150 newton meters of torque provided by the power turret. The ability to execute all of those complex geometries in a single setup will permanently transform your factory's workflow.
It essentially changes the entire definition of what your factory is mechanically capable of producing.
It does, but this raises an important question. Something for you to really ponder as you look at your own factory floor.
Okay.
We have extensively detailed how a power turret's one-time clamping capability completely eliminates the need for secondary milling machines. So if single CNC lathe machines can now simultaneously turn, mill, drill, and tap flawlessly, all backed by massive torque and extreme rigidity, how will this all-in-one evolution ultimately shrink the physical footprint of future factories?
That's a fascinating point.
Right. If you can confidently execute every operation within one single machine enclosure, will the traditional standalone milling machine eventually become completely obsolete on the modern production floor?
Wow. That is a staggering thought to leave on. You secure that highly profitable manufacturing contract we discussed at the beginning, but instead of spending millions to build out a massive, sprawling assembly line of a dozen different interconnected machines.
You just buy one.
Exactly. You just buy one highly capable lathe equipped with the right turret, and it quietly does the work of 3 machines in half the physical space. It completely reframes how you look at the future of manufacturing capacity. Thank you for joining us on this deep dive, and as always, keep learning.